We're going to be looking at the different types of relationships, direct relationships and inverse relationships. For a direct relationship, it might look something like y equals kx. So the variables y and x have a direct relationship by the constant of proportionality called k. It is easy to recognize a direct relationship because it looks linear. As a graph, this might appear something like a line like this, through the origin. That's a bad drawing. An inverse relationship looks like this, y equals k over x, where the constant is divided by the variable that we're considering. And as a graph, an inverse would look like that, and it actually has two parts, so it's a two-part graph for inverse. So let's look at a couple examples and decide whether they are direct, inverse, or neither. The first example has that 50 times p, so it looks like it would be direct, but because there's an extra part added or subtracted on there, this makes it neither. That y-intercept ruins it from being direct. Our next example is, in fact, direct. C is directly related to R, and it has a constant of proportionality that is the part in front of the variable. In this case, the constant is 2 pi. In our next example, this one also looks like a direct relationship because y equals 2 next to the x. It looks very linear, but this exponent of -3 causes us trouble. Negative exponents make you do the reciprocal, turn it into a fraction. So this is really y equals 2 over x to the third. The reciprocal of that to make a positive exponent, and now this is a inverse relationship. And the constant of proportionality in this case is the 2. It doesn't matter that the x was to the third power, it still is an inverse relationship. Next example, I see the variable for x is in the denominator, which means this would be an example of an inverse relationship. The constant of proportionality is everything in front of the x variable. So this time the constant proportionality is 160 over pi. If we wanted to read this, we would say I is inversely proportional to x squared with constant of proportionality 160 divided by pi. Next example, number 5, the exponent is the variable. That's neither linear nor inverse or direct. So we're going to say that this is also neither. This is considered exponential decay. The last one, I see a fraction, but you have to look at where the variable is. The variable is r to the third. It's in the numerator. This is therefore a direct relationship. The constant of proportionality is everything that comes in front of the r. So it's 4 pi over 3. And we would say as a sentence, V is directly proportional to the cube of r with constant of proportionality 4 pi over 3. Let's continue our understanding of direct and inverse by considering some graphs. Graph A is a straight line, a linear graph, so that would be y equals 1.5x. Graph D is a parabola, x squared, so that would be the 0.5x squared. X to the third, that is an S-shaped graph. That is C. Each of those three were all direct relationships. You can tell because there's only one curve on the screen, whether it be the straight line, the shaped parabola, or the S-shaped to the third power. However, the inverse relationships, you can see two arcs on the screen. X to the third power, 1 over as an inverse, has two arcs, and x squared has two arcs, but both are on the top. We call it a volcano graph. Make sure you can recognize differences between each of these graphs and their matching type of function. A couple more things in terms of direct and inverse is writing an equation for a situation. So we have the volume of a cylinder is directly proportional to the height and the square of its radius. So we're going to have V equals, and because it's a direct relationship, I won't have a fraction, everything will be multiplied. I'm going to have some constant of proportionality, and V is proportional directly to H and the square of its radius, so radius squared. V equals KHR squared. Try another. Force required to lift an object with a lever is directly proportional to the mass and inversely proportional to the length. So this time I'm going to have force equals constant proportionality. Now, to make it directly to mass, I will multiply by m, and to make it inverse, I would have to divide by the length of L, so that the variable L is in the denominator of the fraction. The last skill we need is to rearrange situations. Currently, L equals P over M, meaning L is directly related to P and inversely related to M. If we wanted to solve for P, undo the dividing by M by multiplying both sides of the equation by M. M divided by M cancels out, and we end up with P equals M times L. Now we have solved for P. P is directly related to M and L. From here, we could also solve for M. ML equals P. Get M alone, divide by L on both sides, and we get M equals P over L. Therefore, M is directly related to P and inversely related to L. Last question, what happens to L as M decreases? If we looked at our original equation, L equals P over M, if the variable M were to decrease, meaning get smaller, the denominator would be getting smaller and smaller. Eventually, it's going to reach 0.1, 0.001, and any number for P divided by a very small number will make L get increasingly large. So as M decreases, as the denominator decreases, L is going to increase. And vice versa. If P was to decrease, if my numerator got smaller and smaller, all the way down to 1 divided by some big number for M, then my answer is going to also get smaller. So as P decreases, L would decrease. This is the example of what might happen for direct and inverse relationships.